Hello everyone, I'd like to thank you, the organizer, for inviting me to speak here. It's a very interesting and inspiring conference, and I meet a lot of old and new friends. And now today, my half-hour talk it's a follow-up work about what Xiaogang has proposed, this symmetry TO, symmetry TFT construction. But I want to talk about application to a lattice problem and in generic dimensions. And so far, in this talk, I only report our result on gap spaces. There's also still ongoing work for what we can do for gapless spaces. And in particular, the object I want to discuss today is about defects and excitations in so-called invertible phases. And well, invertible phases, it's just some invertible topological phases which the bulk is kind of trivial, but they always have some non-trivial boundaries. And the important feature is that you can always find an inverse of this phase, such that if you stack them two together, you get a trivial phase. And then there are so many examples like topological insulators, P plus IP insulators, P plus IP superconductors, and SPD phases. And but in this talk, I want to talk about the bulk excitations in this kind of phase of matter. And especially there can be line defects or surface defects, those kind of higher dimensional defects. And I would like to summarize their properties what we will conclude as this low entanglement excitations. So this is work that's going to appear soon with my two collaborators. One is David Stephen from UC Boulder, and another is Xie Chen from Caltech. So let's begin with some familiar higher dimensional excitations and defects. The first one is we consider the Ising ferromagnetic states, and obviously everyone knows that the most non-trivial characteristic objects in it is this kind of domain wall, which you use a two-dimensional operator to create this kind of one-dimensional defects in, starting from the symmetry breaking ground state. And another popular, interesting one is this in, say, deconfined phase of the G gauge theory. The ground state has a G topological order, but the key feature of this is that the topological excitations can be loop-like, and it will break non-trivially with the particle. And then that defines a statistical phase, which is a defining property of this phase of matter. So we have to include all these kind of higher dimensional excitations into our study to characterize the phases. So now let's summarize but they're obviously not point-like defects. So we have to, in general, find new ways to study them. And so far, how we do that? First, we sometimes generate it in different ways. We can either modify the Hamiltonians, say modifying the Hamiltonians, the coupling constant along the loop, it becomes change from positive to negative. Or sometimes we start from a particular ground state and use some unitary operator, which is usually non-local operators that to create them from the ground state. And when we study them, we actually don't care about that they may not necessarily be our energy eigenstates. As long as they are good enough to maintain their form for some finite amount of time, then they usually play an important role in our system. But a crucial feature that even though these states, their energy can be extensive and high in the spectrum, but a crucial feature is that you can always get them from modifying a gapped Hamiltonian. And after the modification, the Hamiltonian is still gapped. That means this kind of excitation is, as a ground state, the modified Hamiltonian is still satisfied entanglement area law. So low entanglement is a big feature of this excitations that can be of arbitrary dimension. So that's the key feature we want to keep track of when we describe such a kind of excitations. And then realizing that, we realize also a lot of defects, not just excitations, also shares almost all of these properties. For example, in recent years, an interesting one is this kind of EM exchange symmetry in torical models. So it's a particular line and defects. Through that line, anions gets exchanged. And there's lattice models to tell you that it satisfies all these properties. So now I want to find a unified definition to include all these excitations and defects, basically to treat them in the same way. And especially, I want to only keep track of those with low entanglements. And then so how can I get a unified definition? So our proposal is to use quantum circuits to create or define k-dimensional excitations. So then the first obvious property is that it should be a gap to a ground state of a Hamiltonian that is only modified. That is only modified along these excitations. For example, in the Ising ferromagnet, I am allowed to change my coupling constant along this loop. Then this modified Hamiltonian will have this domain wall as the ground state. And then, okay, I have this way to create it. What's the equivalence class? What are two that are the same? And to define that, we get motivated by a definition that defines what are two phases that are the same. We have this modern definition that two states, they're in the same phase if they can be connected by a finite depth quantum circuit in the same dimension. So that tells us finite depth local unitary does nothing non-trivial. It always connects two states that have share the same interesting properties. So we can use that to motivate our definition. Two excitations, they're equivalent if they're related by k-dimensional finite depth quantum circuit. And then obviously the trivial ones are those created from the bulk ground state by a k-dimensional finite depth quantum circuit. And then what's the non-trivial ones? Then we need to find a way to bypass that trivial ones. And there's two ways to bypass that. First, you use the quantum circuit that's in k+1 dimension. That is how we generate this domain wall defect. We actually use the 2D finite depth quantum circuit to generate this one-dimensional excitations. And the second way to get around it is you still have a k-dimensional circuit, but it's no longer finite depth. You allow yourself to use a linear depth circuit. However, linear depth circuit usually is too powerful. It can almost create any states. Then a nice linear depth circuit is this so-called sequential circuit. So in each step, you only apply a local circuit and you apply it in a sequential way. So the key feature is that after this circuit, each qubit is only applied by a finite number of gates. That's why if you do any cut in this system, the cut will only cut through a finite number of gates. So the entanglement never grows very much. It always keeps the area law. So in this way, we can say, no, so non-trivial ones, they cannot be created by k-dimensional finite depth quantum circuit, but they can be created either by a k+1 dimensional circuit or a k-dimensional circuit, that linear depth sequential circuit. And the example I've shown you, this domain wall, it can be created by a two-dimensional finite depth local unitary. And then this loop excitation can also be created by a two-dimensional finite depth quantum circuit. Then we can, okay, then another non-trivial example is this line defect that I just talked about, this EM exchange defect. So yes, as we checked, some authors checked that first you have a linear depth sequential circuit. So in each step you apply this, you want to get a line defect. So you apply this local gate in a sequential way along this line. And in each step, you only act, say, on some plaquettes. And then you can find that the anyons, if you get an E anyon, that the E line going through, it will become the X line, and it becomes an M type. And then also, the same defects can also be created by a two-dimensional finite depth local unitary, which usually is called this pump unitary, because what it does is that it's a three-step local unitary applying on a surface. And in the end, it does trivial things within this 2D surface, but it pumps a defect to the boundary of it. That's why it gets its name. And we can, another interesting example is this line defect, starting with some trivial product states. Say an interesting defect is so-called on this line, the symmetry is actually broken. So we want to get this GHZ state. Then indeed there's a one-dimensional sequential circuit that allows you to do that. So now we have a circuit definition of our excitations. This is a very operational definition. So then we can ask, just use this definition. Can we classify all the low entanglement excitations? And so let's start with the simplest case. If we have a trivial product state, let's say, what are all the possible excitations we can get? And then you found that it's, since it's trivial, and you found you can only get these two types of non-trivial excitations. So the zero-dimensional excitations must be this Z2 charge. It's created by a 1D finite depth local unitary. And the one-dimensional circuit, it's this GHZ state, and it has to be created by a 1D sequential quantum circuit. So this is just starting a trivial ground state. What about if we start with some entangled ground state? So the key result I want to show is that we have a claim that all these low entanglement excitations in an invertible phase, we know how to work with that. We found that they are in one-to-one correspondence with those low entanglement excitations in a trivial product state. For example, if you care about starting with a ground state that's a Z2 SPT state, my claim is that the zero-dimensional excitation you can find is still only is Z2 charge, and the one-dimensional you can find is still this one-dimensional symmetry breaking state. There's nothing else you can find. And this also works on other examples for KITP chains or P plus IP superconductors. So now let me show you our how we get these results using this symmetry TO TFT construction that Xiaogang has discussed. But I will focus how to use it on the lattice. So the first step, we were going to study the boundaries of topological orders. In particular, we will compare different boundaries of topological orders. They are related by some non-trivial properties, especially if you have a topological order with a particular gapped boundary of your choice. In many, many cases, we can find a finite depth circuit that actually it acts trivially in the bulk, means that it's actually an emergent symmetry in the bulk. It's some logical qubits on the logical space. But once your topological order has an open boundary, it's no longer a symmetry. It's broken in many cases explicitly on the boundary. So so you will change the boundary type. Nevertheless, this is true are related by this circuit, which means that the boundaries will have a non-trivial defect that's created. So these two are have an intimate relation that's in the end related to invertible phases. And then after describing that, I will tell you how to use them, how to use this topological order with boundaries to construct invertible phases, and then use the property of the finite depth circuit to compare the excitations. So still, let's start with the simplest example, this Toricode model. One of the obvious gapped boundaries is this E-condensed boundary. And another one is this M-anion condensed boundary. So let's ask, how can we change the boundary condition from one to another? And the answer is there is a 2D circuit, which I just reviewed, that can change the boundary condition type. And indeed, if your Toricode is defined on the torus, this is a Hadamard gate, but since it has an open boundary, it changed the boundary condition. So then I want to say, pointing out that there is no experiments you can do that only near the boundary that can let you to distinguish the two boundary conditions. Basically, if you only allow to use operators near the boundary, you can never tell whether you are in an E-condensed boundary or M-condensed boundary, because if you use any operators of a K, that's supported on the K dimension to do some experiments on the boundary and read out the expectation value, say, and then you can use this 2D finite depth circuit to get a corresponding operator, which is also K dimension and near the boundary. And these two, because they are related by this finite depth local unitary, the result is the same. And the support of this defect is also the same. So there's no way to tell only near the boundary which one is which. So that means if you only handle one boundary condition, there's no absolute difference between these two as they are related by a finite depth quantum circuit. Nevertheless, we know there must be two different boundary conditions because if we put them two together, and then there will be a domain wall in the middle. And this domain wall is always non-trivial. And in this particular example, if you put this, you create this kind of geometry such that the two parallel is M condensed, another two parallels E condensed, then you create 4 domain walls, and then you can find that this states always have a degeneracy, a ground state degeneracy of 2, which can never be removed by any local operators. That means there's a degeneracy that's encoded in this domain wall. So it's a non-trivial one that can never be removed. And because of so, these two can never be the same type of boundary. So the summary here is that if we, in a topological order, find an invertible line defect in this 2D case, or some invertible codimensional 1 defect, it means that this topological order has an emergent symmetry that can be generated by a finite depth quantum circuit. And then, in many cases, this will no longer act as symmetry on the boundary, so it will change the boundary type. But the two boundary type related as so, they are only relatively distinguished. So they can generate boundaries that are actually twins. So then that's the torical example. Let's talk about another. There's actually abundant of examples of this. Then, for example, in the 3D toric code, we can have this. The 3D toric code has this loop excitations that I have mentioned about. You can let it condense on the boundary. That gives you a gapped boundary condition. And then in 3D toric code, there's also an emergent Z2 symmetry. This is sometimes named as a gauged Z2 SPT defect. Basically, on a bubble, you can find a 3D finite unitary on the surface of this bubble. It's created gauged Z2 SPT defects. And this is also a very well-behaved Z2 symmetry of the toric code. Nevertheless, if you exit on the boundary, the boundary is actually not invariant. And you can check through some lattice that this changed to another boundary conditions. But it's so hard to tell what's or which one is which because they're not there's no absolute distinguish between them. But nevertheless, if you put two together, there's also a non-trivial domain wall between it. In particular, if you create such kind of a geometry, the left is this M condensed boundary, the right is this twisted M condensed boundary, and then you bring a flux loop to the boundary. The flux loop can now become a string, and the endpoint can terminate on the surface. And then you create two of them, and let one winds through another in this kind of 3-loop gradient geometry. Then you always get a phase factor -1 that can never be removed. That tells you that this is a non-trivial domain wall that cannot never be removed by applying 1D circuit only on this domain wall.
So when you do grading, you only grade one pair, not both pair together? In this picture.
Both pair?
Because now you have 2 pairs.
I bring them together.
You're grading 2 together, or just grading 1 pair?
I bring 2 together.
Oh, grading 2 together.
Yeah, and this one, the endpoint is bosonic. It doesn't contribute any phase.
I see.
But this one, it's semionic, so it contributes a -1 phase.
But you don't know which one is boson, which one is second.
Yeah, you don't know. So the message that if we have a finite depth circuit that generates an emergent symmetry in the bulk, it will twist the boundary and this two boundary conditions related by this finite depth circuit, they can only be relatively distinct. And now we can use this knowledge to construct invertible phases using this so-called sandwich construction. So this symmetry TO, TFT construction nowadays has too many names. Some topological holography, topological symmetry, sandwich construction, and I don't know which one to pick. So, but the main message, as Xiaogang said, that if you have a topological order, you care about only its boundary. The block is put to the ground state. And then you found that this boundary is exactly the same as a symmetric sector of a D-1 dimensional system with a global symmetry. And then you can, what's the way to like get from this boundary system to get back to a D-1 dimensional genuine system? And then this so-called this sandwich construction. Basically, in the block, you have some topological orders, and on top, you fix your boundary condition to be some particular gap boundary condition. In this case, I choose this E-condensed boundary. Then what happens is that this like string operator of E anyons, now it's a quasi-local operator in this quasi-1D system. And because the E is condensed on top, it actually only creates excitation on the boundaries. And this E is satisfy the fusion rule like E times E equals 1. So it's a Z2 fusion rule. Then this whole system actually will reduce to a quasi-1D system with only Z2 symmetry. And indeed, you can check on the lattice, like if you send the top and bulk to some, you send to the ground state by using as many stabilizers as you want, and then this E string will, then all the rest operators can find their correspondence in a 1D chain. For example, this E string tunneling operator becomes a single Z operator in a 1D chain, and this kind of truncated star term becomes a single X, and this kind of single E anion creation operator on the bottom becomes a double Z. So in the end, you can recover all possible local operators you can write in a 1D system with Z2 symmetry. And then, for example, we can, if you care about a particular 1D system with some phases, for example, you can send this block also to this E-condensed phase. Then you squash this, and then through this operator mapping, you will figure out that we get a 1D system in the symmetry breaking phase. And then this construction also works for fermion condensed boundaries. For example, you have 2D toric code. If you allow physical fermions, then the fermion emergent fermion can bound with the physical fermion and condense together. Indeed, you can find some exact solvable models to capture that. And then through the sandwich, you are reduced to a 1D system with a Z2 fermion parity symmetry. So this is a one-dimensional fermionic system. And you can also get some operator mapping by this, and you figure out that this, you can write all possible fermion bilinears this way. And in particular, for example, let's do an exercise. If we bound, the top is fermion condensed, and now we send the bottom to be E condensed, and then use that operator mapping, you will find that this one will be a 1D system that is symmetric under this Z2 fermion parity symmetry. And then you can also twist your bottom boundary to this M condensed by 1 by using that 2D finite depth local unitary. And then to do this squashing again, you will get another system with still symmetric under the Z2 fermion parity symmetry. And through the exact calculation, you can find that, yes, we have two phases respecting fermion parity symmetry. One is the trivial superconductor, the other is this KITP chain system. And the point that you don't know which one is which. However, by a particular microscopic choice, of course, as long as you choose some microscopic way to realize it, you already fix some reference. And then, for example, in our reference, we found that this one will reduce to a trivial superconductor, and then by another one, which is related by this EM exchange defects, it will automatically become this KITP chain state. And then I can reach my conclusion comparing the excitations. Because we know that this right-hand side, we get this bottom boundary condition by acting it by a 2D finite depth quantum circuit only, so it does only non-trivial things on the bottom boundary. Then whatever symmetric operators I care in this left trivial superconductor, I can create this by some local operators only near this bottom boundary. Then through this finite depth local unitary, it also becomes some other operators near the bottom boundary, near this twisted boundary condition. So in this way, through this construction, wherever symmetric operators here, I can find the unitary and then use that to find the corresponding symmetric operators that are on the right-hand side. So I establish one-to-one correspondence between the symmetric operators. And then those low entanglement excitations are a subset of those symmetric operators. So then they also have a one-to-one correspondence. So in the end, the message is that if we only allow you to use bulk Hamiltonian symmetric operators, you can never tell which one is which. And then using the 3D examples, if you have this flux condensed boundary on the bottom boundary, then after squashing, you get a, sorry, I have a typo here. It's a 2D system with a Z2 symmetry. And if you twist the bottom boundary condition, and you will get a 2D system with, that has a SPT order. And these two are also, their low entanglement excitations also have one-to-one correspondence. And with that, I can end my talk.
Thanks for leaving enough time for discussions. Max.
I'm a little confused. So say I have a P plus IP superconductor, right? And I look at the pi flux vortex, right? That has a excitation which is a Majorana. So would you say that that's in one-to-one correspondence with a pi flux vortex in an ordinary superconductor?
It has one-to-one correspondence with 1D excited. Okay, flux you can in P plus 1D you can generate it using circuit. You have a 1D circuit. Yes. That generates this. So you have two endpoints, that's the pi flux. And then in the trivial superconductor, you also have a 1D low entanglement excitation. It's just the KITP chain defect, which I can use either the sequential circuit. It should use the 1D sequential circuit to generate it.
I see.
Yeah, so 1D, the only one non-trivial 1D excitations in a trivial superconductor is this KITP chain defect. And it's corresponding to this flux line defect in the P plus IP.
I see. Thank you.
Yeah, looks like you give many examples that whenever you have a transparent invertible domain wall in a bulk, that would give you attach that to the boundary, that give you the SPT state on the boundary. Yeah. Yeah, here just want to make a comment that's this picture seems is more general, very general in the sense even when you have a non-invertible symmetry, you have an arbitrary CMTO in the bulk, then even in that case, the invertible domain wall in the bulk will correspond to this SPT of this non-invertible symmetry. Yeah, this yeah, this feature probably is a very general feature applied to non-invertible symmetry.
Yeah, we hope to apply to include the non-invertible cases. But even for invertible symmetries, I only talk about how we get invertible faces. But on the top boundary, if I choose some other things, through the sandwich, I can actually get some non-invertible faces. So actually, we can use that to describe excitations in non-invertible phases, but the conclusion is, it's a little bit involved. So.
But since you apply your idea to for the low entanglement excitation in the trivial phase and SPT phase, if you apply this to the non-trivial topology order phase, whether there's some difficulty or challenging, I mean, can one classify all the low entanglement excitation in even topology order phase? Yeah.
So far our finding is that you will classify excitations in non-invertible phases according to the emergent symmetry. For example, in toric code, 2D toric, you can use the 3D toric code to construct a 2D toric code through the sandwich. And then you all need to keep track of this one-form symmetry. And you say that if I keep track of this one-form symmetry, and now I do not allow it to break explicitly, and then the excitations also has a mapping.
Nice. Okay, thank you.
Yeah. It's not necessary. There's other arguments that can reach the same conclusion for especially the bosonic SPT phase and KITP chain defect.
So in the 3D case, you have two boundary states, right? And then one of them is essentially the other one together with the Z2 SPT. And if I'm allowing fermions in the system, am I allowed to have a P plus IP on one side, instead of a Z2 SPT? And would that consider a low entanglement excitation by, say, the standard of local unitary quantum circuits?
That's a very good question. This construct generically should work, but so far the P plus IP defect pump operator is not as nice as other pump operator. It's not a finite depth local. It's only quasi-local, and because of that, there's have some subtleties in it. We think it should work, but we have to check it more explicitly. But if at TQFT level, it is an invertible defect, and it does twist your boundary conditions. Yeah, if you only don't care about that, it's a totally well-defined invertible defect.
Thank you.
Questions?
Wenjie, could you clarify what you mean when you say the trivial and SPT state cannot be distinguished by symmetric operators or something like that?
Oh, I mean, if you're only within the trivial state, you only use some symmetric operators of any dimension, then any experimental results you can get, I can provide you similar experiments in SPT, and you'll get the same results. So you can never tell you are in a trivial phase or SPT phase. So, just by using the bulk excitation itself without, say, reference to other states or boundaries.
So you're not talking about like calculating expectation values of symmetric operators?
Symmetric operators. I am talking about the expectation values of symmetric operators.
But if you take the trivial paramagnet and the cluster state, and if I measure the expectation value of X on one side?
Yes, but then I will find a corresponding operator which is not product of X. It's a product from other operators that give you the same result, but it's still a symmetry.
Thank you.
So when you defined non-trivial excitations in k dimensions, you had two different definitions, one using k plus one dimensional quantum circuits and one using linear depth sequential circuits. So you gave some examples where those are sort of equivalent. Are they obviously always equivalent? And is it also obvious that we should never consider, say, k plus two dimensional circuits or something like that as a different class of potential excitations?
Very good question. I think the answer is so far all the example we care about, there's not. We don't need a k plus two dimensional circuit, and there are some defects. You can only find k plus one dimensional circuit, but not a sequential circuit. I think. For example, domain walls, I think is, but of course, domain wall is a non-trivial excitation only in the symmetry breaking phase. I think that's, yeah, you don't have sequential circuit to get that.
Thanks.
Okay, other questions?
Yeah, this kind of interesting point. That is, you say the domain wall in the symmetry breaking phase need to be created by the like a one higher dimensional finite depth circuit. However, you can do a duality transformation. In the dual model, it will be able, you can create it by the maybe sequential circuit.
So in the dual model, you mean dual to a symmetric
Gauging,
state?
if you do the, if you gauge the Z2, you get a dual model.
Yeah.
So I wonder whether this is a general feature that is whether a defect need to be created by the like a one-dimensional defect need to be created by the two-dimensional operator or one-dimensional sequential operator. That's maybe the depend on your UV regulation. When you do this gauging or duality transformation, this feature may switch.
Yeah, in many examples, it does switch, like this Z2 example, but in some example, it probably not switch, like this KITP chain defect. If you gauge the fermion parity, you get Ising model, and then to create this this kind of defect is some sigma line defect, which is still has to be 1D sequential circuit.
Just following the previous question, is that true that to implement a duality, you need a sequential circuit?
No, I'm not talking about how to implement duality. We said that two models are dual to each other. Yeah. Whether the defects that's related by duality, if one is created by a sequential circuit, can it be simplified in the dual model?
Yeah. I mean, just to implement the duality, just a separate question. I'm wondering whether it is necessary to have a sequential circuit. I thought a finite depth circuit cannot do the duality for you. So that's why maybe on one side you need sequential circuit, on the other side you can have finite depths.
Yeah, I just want to confirm. So the bulk have different automorphism for the anion permutation symmetry. They have some EM duality or just relabel the anion. So the relabeling would just correspond to some finite depth unitary on the boundary, and the EM duality would correspond to a sequential quantum circuit on the boundary.
Sorry, is that a question or a statement?
Sorry. No, it's my understanding. I'm not sure whether it's correct or not.
So you mean on the boundary, can it be can I do on the boundary EM exchange symmetry by a finite depth circuit rather than sequential circuit?
I mean, there's a bulk boundary correspondence between the bulk automorphism and the boundaries, whether it's a sequential quantum circuit or a finite depth unitary.
Actually, I think if bulk is a sequential, has to be a sequential circuit. The boundary also, if you only do on the boundary, it also need to be a sequential circuit. For example, in this torical EM exchange on the boundary becomes this Kramer-Wannier duality. It also has to be a 1D sequential circuit.
Okay, cool. I guess let's thank Wenjie again. And we can now go for cookies.